Hello everyone, I'm Takahiro Nishida from Shizuoka Institute of Science and Technology. Today I would like to talk about a presentation. The title is Crack Detection Inside Concrete based on electrical specific resistivity monitored in drying process. First of all, I would like to talk about background of this study. Now, visual observation is a major tool of periodical inspection of port concrete structures. However, quantitative and reliable information is not always obtained from the visual observation. Therefore, non-destructive monitoring systems are required for preventive conservation. In present state, some methods are proposed for monitoring steel corrosion due to chloride attack, such as polarization resistance, half-cell potential, or specific resistivity. In this method, the corrosion rate or corrosion situation are monitored by electrochemical measurements. Also, crack detection is one of the most important factors in the case of monitoring the deterioration due to chloride attack. From background, the objective of this study is to establish a real-time monitoring method of crack detection due to steel corrosion in port concrete structures induced by chloride attack. In this monitoring method, the time-depending change of specific resistivity of concrete during drying process of concrete surface was positively focused on. This figure shows the image of measurement method. There is a concrete surface, and here is a concrete inside the concrete, and we put some electrode to measure the specific resistivity of concrete. There is a current flow electrode and voltage measurement electrode. After charging, after applying the electric current, in the case of no crack case, the electric current flow like this. On the other hand, cracked case, for example, horizontal crack, the electric current flow like this, concentrate on the surface area. On the other hand, vertical crack, the electric current flow like this. In the case of drying process, water evaporates from the surface area, so the change of specific resistivity is depending on the cracking situation. So we can detect the generation of crack or what kind of crack generated in the inside of concrete. This slide shows the outline of specimen. In this study, two types of specimen were used. In type 1 specimen, there are 5 steel bars, and each steel bar has different corrosion situation. These two steel bar no corrosion, and second steel bar, this corroded, slightly corroded. In this case, the weight loss of steel bar due to corrosion is 6 milligram per cubic square meter. Third one is corroded steel bar. In this case, 10 milligram per square centimeter. And last one is heavily corroded. In this case, 60 milligram per square centimeter. This specimen is exposed to laboratory at the 20 degrees Celsius temperature, and dry and wet condition cycle was applied. This corrosion is generated by the electrical corrosion. And type 2 specimen, in this case, the size of specimen is 300, 200, and 200 millimeter, and there is a steel bar. And around steel bar, we put the electrode to evaluate the polarization resistance. Also, on the surface of concrete, we put the electrode to measure the specific concrete resistivity. This specimen was exposed to outside environment. This slide shows the measurement method of specific resistivity of concrete. We use the Wenner method to measure the specific resistivity and put the current electrode and voltage measurement electrode like this. From this equation, we can obtain the specific resistivity of concrete. And rate of specific resistivity change during drying process, RSRC, was monitored during corrosion process, during drying process like this. This slide shows the result of laboratory test. The specimen, type 1 specimen, was exposed to the submerged situation, and after drying the specimen, we measure the specific resistivity. This graph shows the relationship between the specific resistivity and drying time. From this result, specific resistivity increased with drying time increasing. Also, the specific resistivity change increases with corrosion progressing. Especially in the case of heavy corrosion, the specific resistivity becomes highest. In the drying process, the rate of water evaporation follows the diffusion law. In this case, the rate of water evaporation is proportional to the root of time. Considering this, the result of laboratory test was converted to specific relationship between specific resistivity and root of drying time. When we focus on this area, the relation becomes proportional, and using this slope, we calculate the rate of specific resistivity change, RSRC, like this. This graph shows the RSRC in each corrosion situation. This is no crack situation, slight corrosion, corrosion, and heavy corrosion. From this result, the corrosion situation can be detected using RSRC. After the laboratory test, we cut the specimen and check the cracking situation. This is no crack situation, no corrosion situation, and we can find any crack. We cannot find any crack inside of concrete. On the other hand, in the case of slight corrosion, we found horizontal crack, and corroded situation and heavy corroded situation, we found horizontal and vertical cracking. So, considering the concept of our measurement method, the RSRC increases with the corrosion situation, depending on the corrosion situation, and it comes from due to the generation of inside crack. To verify the laboratory test, we also conducted the outside exposure test. The specimen, type 2 specimen, were exposed to the seawater sprayed situation like this, and monitoring the specific resistivity of concrete from the surface. In the outside, the resistivity also influenced by the temperature. So the influence of temperature is corrected by Arrhenius law. And corrosion rate is continuously measured by the embedded corrosion sensor like this. In order to remove the temperature effect, we consider the Arrhenius equation. So this is the result of Arrhenius plot. And we calculate the activation energy of specific resistivity of concrete. Then, considering the Arrhenius equation, the influence of temperature is corrected like this. So black result is before correcting, and the red one is after correcting the temperature effect. This graph shows the relationship between the RSRC and exposure time, and this is the result plot. And the RSRC of slight corrosion is 22, so obtained result is much lower, and it is considered that there is no corrosion and no cracking. And also we monitored the polarization resistance and calculate the weight loss of steel bar due to corrosion during test. So in this case also the corrosion is very low. However, these two plot is relatively high comparing to the other data, and check the humidity on this day. So we found that this day humidity is very low. So this is the relationship between the RSRC and average water content in the air. In the case of 2 days, very low water content in the air. So we conclude that there is a possibility that the RSRC can non-destructively evaluate the corrosion progress of steel bars in concrete. However, we should also consider the humidity effect. So continuous investigation will be conducted. Finally, I would like to talk about the conclusion of this study. First, RSRC of concrete surface increases by the generation of crack due to corrosion, because the water evaporation speed might be changed due to existence of crack, and resistivity rapidly increased in the case of cracked concrete. Second, the relationship between specific resistivity of concrete and temperature is explained by Arrhenius equation, and its activation energy was obtained as 3.7 kilocalorie per mole. Third, RSRC increased with time as well as increase of weight loss of steel bar due to corrosion. Thank you for your kind attention, and if you have questions, please contact me through email or our Facebook page.